In this video, we'll demonstrate the impact of the size of the training dataset on the quality of the mapping function and the estimated performance of a fit neural network model. The challenge in making an effective and useful deep learning model is knowing the correct size of the dataset to use. Using a dataset which is too small will effectively result in the model creating oversimplified results on all levels, meaning it's only effective for the bare minimum of applications. On the other hand, using a dataset which is too large may create too many levels for any of them to have any real practical use. So let's look at a simple two-class or binary classification problem. In the first code cell, we have imported all the essential libraries. In line 1, we have the SkillKit Learn library, which provides the make_circles function that can be used to create a binary classification problem with a prescribed number of samples and statistical noise. Next, in line 2 and 3, we've imported where from NumPy and Pylot from matplotlib for plotting. In the second code, we'll have the scatter plot of the circled dataset with the given amount of noise. In line 1, we've defined a function called circle_problem, which will create a dataset with the given amount of noise_value. In line 2, we use the make_circles function library provided by SkillKit Learn to create a binary classification problem with a prescribed number of samples and statistical noise. As we can see, we have two input variables that define the x and y coordinates of the point of two-dimensional plane. The points are arranged in two concentric circles for the two classes. Next, the seed for the pseudo-random number generator is specified using the random_state argument that allows the exact same points to be sampled each time the function is called. Then, in line 3, we select the indices of samples in the y array that have given value using the where_numpy function, and then use those indices to select rows in the x array. Following this, in lines 4 and 5, using the scatter matplotlib function, we create the scatter plot using all input samples for class 0 with the color red and all points for class 1 with the color green. Now, all real data has statistical noise. With higher statistical noise, the problem becomes more challenging for the learning algorithm to map the input variables to the output or target variables. So, in line 7, we defined a set of Gaussian noise, which will be the pass to the noise argument that defines the standard deviation of the noise, where 0.0 indicates no noise or points drawn exactly from the circles. From line 8 to 11, we iterate through the 4 scatter plots as subplots using the subplot matplotlib function in a 4x4 matrix with the noise values. Finally, in line 12, we called the show function to display the scatter plots. Now, the third code cell, we created a similar plot of the problem with a varied number of samples. Higher samples give a learning algorithm with greater opportunity to understand the underlying mapping of inputs to outputs, and, in turn, a better performing model. As we can observe in line 7, we updated the circles_problem function to take the number of samples to generate as an argument, as well as the amount of noise, and set a default for the noise at 0.1 in line 1, which makes the problem noisy, but not too noisy. Let's run the program. To do that, click on the Runtime menu and select Run All. As we can observe, a plot is created with 4 subplots for each of the examples. For the plot with varied noise, we can observe that it has created one plot for each of the 4 different noise values, 0.0, 0.1, 0.2, and 0.3 in the top left, top right, bottom left, and bottom right respectively. As we can observe, a noise value of 0.0 is not realistic, and a data set so perfect would not require machine learning. However, the small amount of noise value of 0.1 makes the problem challenging, but still distinguishable. A noise value of 0.2 makes the problem very challenging, and a value of 0.3 makes the problem too challenging to learn. As for the plot with varied sample size, we can see that 50 points are probably too few. However, 300 points appear sufficient to really learn the problem. The plot suggests that 400 and 1,000 examples may be significantly easier to learn, although hide the fact that many outlier points result in overlaps between the two circles. And this is how we can study the impact of the size of the training dataset on the quality of the mapping function and the estimated performance of a fit neural network model.